Something happened with 3I/ATLAS today that's making NASA teams seriously uneasy. They just pushed a fresh update to the official tracking solution. And here's what's wrong. This interstellar comet was supposed to be settling down by now. It passed the sun, it's heading outbound, the heat is dropping. Everything about it should be calming down. But NASA's latest data shows the exact opposite. It changed again overnight. The orbit shifted sideways. New jets opened up. The brightness pattern reconfigured. What's driving these constant changes? Let's dive right in. Here's what happened in the last 24 hours and why it's got mission teams on edge. Every day, NASA and observatories worldwide feed measurements of 3I/ATLAS into an orbit solver. This sophisticated software takes raw position data and calculates where the comet should be next. You give it where you saw the object, when you saw it, and all the gravitational forces from the sun and planets. The software processes everything and tells you where to point your telescopes tomorrow, next week, next month. When the model understands what's happening, the differences between prediction and reality stay small and random. These differences are called residuals, basically your margin of error. If everything works correctly, residuals bounce around. Sometimes the comet runs slightly ahead, sometimes behind, sometimes left, sometimes right. It all averages out over time. Today's data didn't average out. When teams plugged in where they actually observed the comet in the last 24 hours, those measurements didn't scatter randomly around the old prediction like they should have. They leaned. Every single fresh position sat slightly off to the same side. The comet had quietly drifted across its projected track since yesterday's update. That's your first clue something changed, and it's baked right into the numbers themselves. To make the model fit reality again, the team had to adjust what are called non-gravitational parameters. This is the part of the equation that accounts for jets of gas and dust, giving the comet tiny rocket pushes. Comets aren't dead rocks floating through space. They're active bodies constantly venting material. When gas shoots out in one direction, basic physics says the comet must push in the opposite direction. Yesterday's solution calculated a specific thrust, strength, and direction from these jets. Today's solution needs completely different values. The updated calculations show 3I/ATLAS is now experiencing stronger sideways acceleration than before. Not catastrophic, not veering toward Earth, but absolutely real and measurable. The comet is pushing itself in a different direction today than it was yesterday. Something about its internal activity pattern shifted overnight. And here's what makes this unsettling. We're past perihelion. The comet already made its closest approach to the sun. It's moving outbound now. Solar heating is decreasing with every passing day. Everything we know about comet behavior says activity should be winding down at this point, not ramping up in new directions. While the orbit specialists were wrestling with those numbers, the imaging team was running their own comparison, completely independent of the math. They stacked yesterday's deep exposures, combining hours of data to capture as much light as possible. Then they stacked today's images using identical methods. Same instrument, same filters, same tracking. Only the time changed. Then they blinked between the two image sets, watching for any differences that emerged. The overall structure looked familiar at first. You've got the bright inner coma surrounding the nucleus. You've got the extended tail stretching away from the sun. Classic comet anatomy. But when they zoomed into the region immediately around the nucleus itself, that's when the second part of this story revealed itself. The bright core no longer sits comfortably centered in its own glow, the way it did yesterday. In yesterday's data, the inner coma had this slightly flattened oval shape, with the core nestled right along the central ridge. The brightness peak sat exactly where you'd expect it, nicely centered and symmetrical. Today's stack tells a different story entirely. That ridge thickened dramatically on one side and thinned on the other. The brightness peak slid noticeably toward the thick side. It's like someone physically grabbed the entire inner coma and tugged it sideways. The material didn't just get brighter or dimmer uniformly, it redistributed. More gas and dust flowing heavily from one side now, significantly less from another. And there's something else in today's images that wasn't there before. A faint secondary streamer now appears coming off at a completely different angle from the main tail. It's subtle enough that you might miss it with a casual glance. But when you enhance the contrast and really dig into the data, it's clearly there. A fresh thread of material feeding into space from a spot on the nucleus that was either quiet yesterday or much weaker in the previous observations. So now you've got two completely separate pieces of evidence pointing at the exact same conclusion. The math says there's a new sideways push requiring orbit adjustments. The images show the inner coma visibly heavier on one side with what appears to be a new or significantly strengthened jet. Two different teams using completely different techniques and working with different data sets, all arriving at the identical story without coordinating. When that happens, in science, when independent lines of evidence converge like this, that's how you know something real is going on. But there's actually a third piece that makes the whole picture even more compelling. The teams measure how the comet's brightness changes as it rotates, because these objects spin as they move through space. As the nucleus rotates, different parts of the surface point toward us. If one side is venting more actively, you'll see the brightness increase when that region faces you and decrease when it points away. It creates a repeating pattern in what's called the light curve. Yesterday's light curve showed a pattern that matched the slightly accelerated rotation period they'd been tracking for several days. One main brightness peak, one smaller bump, overall familiar. It's exactly what you'd expect from a comet with one dominant active region and maybe one or two much smaller secondary vents. Today, when they folded the new brightness measurements over that same rotation period, the pattern completely broke down. The main peak shifted its timing in the rotation cycle. It's arriving either earlier or later than it should, based on yesterday's data. Even more striking, that smaller bump grew into something nearly equal in height to what used to be the main peak. Now it looks like a clear double peak per rotation instead of big peak, little peak. That's the unmistakable signature of a second active region suddenly becoming just as important as the first one, or a completely new vent opening up on the surface. Two strong activity sources positioned on different parts of the rotating nucleus means two distinct brightness peaks as the comet spins, and each region faces us in turn. When you put all three of these pieces together, here's what you're seeing. The official orbit solution required updating because the comet moved sideways relative to where predictions said it should be. The inner coma appears visibly lopsided in the newest images, with one distinctly thicker side and a new streamer. The rotation light curve now shows two strong brightness sources instead of one dominant region. This isn't a single dramatic explosion. The comet didn't split in half or suddenly flare 10 times brighter. This is something quieter but potentially more significant. It's a reconfiguration. 3I/ATLAS updated its own internal configuration, and we're detecting the effects through multiple completely independent measurement techniques. So what's actually happening inside this object? The heat from its close dive past the sun is still migrating inward through the nucleus. This is slow physics, not instant. The outer crust responded first, because that's what solar radiation hit directly. Those outer layers started venting the easy ices, the volatile materials that sublimate at relatively low temperatures. But now that wave of thermal energy is finally reaching deeper layers inside the nucleus, and those deeper layers have different compositions entirely, different mixtures of water ice, carbon dioxide ice, methane, rock particles, and complex organic compounds. Different internal fracture networks, different structural weak points where stress has built up over time. When those deeper pockets finally hit their threshold temperature and start sublimating, they don't necessarily vent from the same surface locations. A completely new crack might open somewhere else on the surface. Maybe there was a structural weak spot there all along, and now the pressure from sublimating gas below has finally built up enough to force that crack open. Or an older stressed fracture that was already there suddenly widens. Maybe it was already venting small amounts, but now it gets significantly bigger and starts pumping out vastly more material. Any of those scenarios instantly changes which parts of the comet's surface are actively venting and exactly how strong those regions are. The whole pattern of where activity happens shifts from one configuration to another. From our perspective, looking through telescopes, that internal change shows up as a shifted brightness peak in the Coma. It appears as a new streamer feeding the tail structure. It reveals itself as a measurably different thrust direction in the orbit calculations. It creates that double-peaked pattern in the light curve as the reconfigured nucleus rotates. The internal plumbing just updated itself. What was producing a strong jet yesterday might be weaker today because that pathway partially closed. What was barely active yesterday might be roaring today because a new vent opened or an old one widened significantly. Here's why this matters beyond just interesting images. It rewrites the physical forces acting on the nucleus itself. Two strong active regions on different sides of a rotating comet means different torque is being applied as it spins. Every time an active region rotates to face the sun and really starts pumping out material, it creates thrust. That thrust tries to either spin the comet faster or slow it down, depending on where that jet is located and which direction it's pointing. Those forces can tweak the rotation rate over time. They can tilt the spin axis itself, gradually changing which parts of the surface get heated most intensely. That changes how future solar heating hits different regions, which changes where future activity happens, which changes the thrust forces again. It's all connected in this feedback loop, continuously feeding back on itself. The longer this continues, the more internal strain builds inside a body already under enormous stress from its passage through the inner solar system. This thing came screaming in from interstellar space, dove close to the sun where it got hammered with intense heat and radiation, and is now trying to adjust to all of that while moving back outward. If activity stabilizes in this new configuration, if these two dominant vents keep running steady without more dramatic changes, then 3I/ATLAS might ride this phase out. It'll slowly fade as it moves farther from the sun and cools down. We watch it drift back into deep space, but if we keep seeing fresh changes every few days, new vents opening, new thrust directions, new internal reconfigurations, then we're watching a nucleus constantly rebalancing under stress it may not be built to handle. History with other comets gives us a reference point here. Shoemaker-Levy 9 broke into over 20 pieces. Linear disintegrated in 2000. Atlas C/2019 Y4 fragmented in 2020. The pattern always starts exactly like this. Small changes, new activity, shifting forces. Then one day something gives. Right now, NASA's language stays careful and measured, but the data speaks clearly. 3I/ATLAS changed again overnight. The models needed updating. The images show it. The math confirms it. And nobody knows if this is the final adjustment or just one more step towards something bigger. That's where we are. That's what today's update tells us. If this has your attention, go ahead and hit that like button, drop a comment with your thoughts, and subscribe to Galactic Breaking News with notifications on so you catch the next development the moment it drops. We're tracking this interstellar visitor day by day, and you won't want to miss what happens next.